Yo, what's up everyone? Welcome to our fifth unit, which is going to be kinetics. Today we're going to learn about reaction rates and rate laws. So remember from last unit, thermodynamics is going to tell us whether or not a reaction occurs. But one of the things that thermodynamics does not tell us is the speed of the reaction. Well, this is what kinetics does. Kinetics is the study of how fast a reaction occurs. So certain reactions like the burning of wood are going to be really, really fast. They're going to happen like almost instantaneously, but other things like rusting are going to happen really, really slowly. And so kinetics helps us explain uh, not only how they go from their products to their reactants, but why they go from their products to reactants at a certain speed. And so there's going to be a lot of factors that affect the rate of reactions. It's going to be the reactant concentration, the surface area, temperature, catalysts, and general environmental factors. So a lot of this is really complicated. Let's just get into like the couple basics today. Consider a reaction where you go from A to B, and you have a system where you start off with 14 A molecules. And as time progresses, as you go halfway, well, now you have 7 red molecules and 7 blue molecules, and at the end you have 14 blue molecules. And so in here we see that A is going to disappear and B is going to appear. And as it turns out, the rate of disappearance of A is going to equal the rate of disappearance of B. However, if we look at a different system, let's say the equation A equals A results in 2B. Well, let's start out with 14 red molecules again. And then as we go halfway, you realize you're left with 7 red, and then 14 blue. And at the end, you just have 28 blues. So in this case, A disappears and B appears, as we saw before. But in this case, it's a little different because the rate of appearance of B is 2 times the rate of appearance of A. And as that turns out, those are stoichiometric coefficients, right? The 2 times the appearance of B represents the 2 that's right here on the B. The 2 that is right here. Sorry, my pen's not on. The 2 that is right here. And so the 2 times the rate of disappearance of A equals the rate of the appearance of B, and those are just stoichiometric ratios. An important thing about reaction rates is their unit. So reaction rates are always going to be in the unit molarity over time. And usually the time factor, it's usually going to be molarity over seconds. That's what's used generally, but you might see it in hours, you might see it in days, based on the reaction. But do know that it's a molarity over time. So for example, if your rate of appearance of A was 1 molar per second, your rate of disappearance would be 2 molar per second. And so again, you can see how these are based on the stoichiometric ratios that we see in the chemical equation. And so let's do a bit of practice. In the reaction, blah, 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 the rate of disappearance of F2 gas is 1 molar per second. What is the rate of appearance of chloride ClF3 gas? Okay, so it's important to recognize the coefficients in this. The F2 has a coefficient of 3, but the ClF3 has a coefficient of 2. This tells us that 2 over 3 times the rate of disappearance of, or rate of appearance of ClF3 is going to equal the rate of disappearance of F2. Remember, these are all just stoichiometric coefficients, and so we know the rate of disappearance of F2. So we can plug that in, and that's going to be 1.0 molarity per second. And if we just solve for ClF3, well, that rate is just going to be 1.0 times 2 over 3, which is just 0.67 molarity per second, which is answer choice B, and I had the answer up the whole time. It is, in fact, the right answer. So again, these are stoichiometric ratios. You just need to remember that. Let's move on to one more question. For the reaction, blah, 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 if NH3 is consumed at a rate of 0.5 molarity per second, at what rate is the water being formed? Well, again, the coefficients for these, NH3 is going to have a coefficient of 4, and H2O is going to have a coefficient of 6. This tells us that 4 over 6 times the rate of appearance of H2O is going to equal the rate of disappearance of NH3. And since we know the rate of disappearance of NH3, we know that's going to be 0.50 molarity per second. We can solve for the rate of appearance of H2O. by just multiplying both sides by 6 over 4. And you just do a little bit of algebra, and you realize it's going to be 3 over 4 molarity per second, which is just 0.75 molarity per second, which is answer choice C, and that is correct. So again, these are stoichiometric, but more than anything, these are relative to each other. As long as you know the rate of one reactant, you can determine the rate of any other reactant or any other product using those stoichiometric ratios. So the reactions that we've been working with up until now are going to be like in the form A to B, and the concentration of A goes down linearly over time. But not all reactants are going to act like this. They're not all going to linearly go down. So although they might, as we see in the one all the way to the left, some of them might go down quite a bit and then plateau off, and some might go down a little and then plateau off. So there's many different ways that reactants can change in their concentrations over time. And the way we represent this is using rate laws. So the rate law is an equation that outputs the rate of a reaction given the concentration of reactants. And so if you had an equation like A plus B results in C plus D, your rate is going to be equal to K, which is some rate constant, times A to the M. M represents the rate order of A, times B to the N. And so N is the rate order of B, with A and B being the concentrations of A and B respectively. M plus N is going to be your overall order of the entire reaction, but there's kind of this ambiguity of what rate order is. Well, those graphs that I put before are not put there randomly. These are going to represent zero order, first order, and second order reactants. So in zero order reactants, their concentration is going to go down linearly over time. In first order reactants, they're going to go down a little and then start plateauing off. And then in second order reactants, they're going to go down a little and then plateau off. So again, rate orders are going to be determined experimentally. What you can't do is look at their stoichiometric coefficients and say those are the rate laws. It doesn't work like that. So how would you actually go about determining the rate orders? Well, one way that you could do it is you could look at something like this trials table. So this is a method in which you do a couple trials with different concentrations of A and B, and you measure their initial rates. To find the rate orders of, let's say, A, you would find instances where B, the concentration of B is held constant. So in trial 2 and 3, the concentration of B is held constant. On the other hand, the rate of A is doubled, or the concentration of A is doubled, but we see the initial rate has not changed at all. It's going to be times 1. And so when the concentration doubles without the rate changing at all, we say that's zeroth order. And like an easy way you could do this is looking at, you see the amount you multiplied by, well, that amount to what power is going to equal the amount you multiplied the initial rate by. And so 2 to the x equals 1, well, x is just going to be equal to 0. Let's try determining the rate order for for B rather. So we would need to keep the concentration of A the same. So in trial 1 and 2, we keep A the same. On the other hand, for B, we double it. And then for initial rate, you see that A quadruples. So we can set up our equation again. The concentration has doubled, so 2 to the x equals, and the initial rate has quadrupled. So what is x? Well, x is going to be 2. So that means that A is 0th order, while B is going to be second order. And so how would you display this in a rate law? Well, rate is going to equal K times the concentration of A to the 0th power times B to the second power. And of course, A to the 0th power is just 1, so you can cancel that out. So your rate really becomes K times B, the concentration of B squared. And that's how you determine a rate law from these initial rates tables. Alright, let's do a bit of practice about rate laws using real questions. So the initial rate of the reaction A plus B to products varies with the initial concentrations of A and B as follows. So remember, our rate is going to be K times the concentration of A to some power times B to some other power. and it's our job to figure out the orders. So in order to find out the order of A, we need to keep the concentration of B the same. We can do that in the first and second rows. We see that A is going to double, and the initial rate is going to double as well. While 2 to the x equals 2, x is just going to equal 1. So that means the rate order of A is going to be 1. Let's look at what the rate order for B is going to be by keeping the concentration of A the same. We can do that from row A and from row 1 and row 3. And so from row 1 to row 3, the concentration of B is going to triple. On the other hand, the initial rate from the first row to the third row is going to be multiplied by 9. So 3 to the x equals 9, well x is just going to equal 2. So that means our rate order for B is going to be 2. And we can plug this information back into our rate law by just plugging in the values for the orders. So 1 and then B to the second power. And as you can tell, that's answer choice D, which is in fact the right answer. So again, the important thing is keeping the concentrations the same and then see how much the other concentration has multiplied by and then relating that to how much the initial rate has multiplied by. And using that, you can find the orders and therefore your rate law. Alright, that's all I have. I hope you learned something and I hope you'll join me for part 2. Thank you. I'll see you later.